Okay, question time. So now let's see what all we've learned. How does it map to answering questions that they'll ask us? They will ask us. So I don't know who this they is, but then whoever's going to ask us, let's just try and play with some of these questions and see, test ourselves as to how much we've learned. The first question, okay. A concave mirror produces a 3 times magnified real image of an object placed 10 centimeters in front of it. Where is the image located? Okay. If I read it that way, right, I'm already beginning to get all bored. A concave mirror produces, okay. Let's just take this and as we read it, represent it and then start solving it. So what is the question saying? A concave mirror. So the moment that's told, I'm just going to, in my head, I'm not going to do this on paper all the time. I'm going to do it in my head. I'm going to imagine a concave mirror produces a 3 times magnified real image. Okay. That sentence tells me that I need a real image. So where must the object be for me to get a real image? It can't be between, the focus and the pole. It has to be beyond that somewhere, because between focus and the pole, I get a virtual image. So it must be somewhere outside of it. So if I take it somewhere over here, I know I could get a magnified real image somewhere over here. Great. I know this. So some 3 times magnified image. And that's what I need. And the object is placed 10 centimeters away. So that distance is 10 centimeters. Great. Now where is the image located? So in my mind, I know that I need to find this one. Great. So we don't have to do all of this. Yeah. What we have shown you here is what we do inside our heads before we jump into what we will usually do, which will tell you what that is. So what have we done here? This is the object. We know how this works, right? One of the rays is going to go like this. Then it's going to come back. Let's say like this. Yeah, we kind of drew the image before itself. Yeah, we kind of jumped the gun that way. But yeah, doesn't matter. And the other, that's one of the rays. The other ray you could trace it down like this, or you could take the other ray. You could use any 2 of these 3 rays for you to be able to get the image of that point, right? Now we're just kind of redoing what we already did as part of our videos. So what have we done here? Taken that point and shown that it can form, its image forms over there. Now why are we doing this? Because if we know the ratio between this and that, we can find the ratio between, let's use a different color, this and this whole length, right? Why? Because if I take this out and draw it out separately, what you'll get are 2 triangles that look like this. Now there's nothing very special about these triangles except for the fact that these 2 angles are equal. Now why are they equal? Because one of the rays we could have taken is this and this, right? Now that means that the angle of incidence must be equal to the angle of reflection. The I must be equal to R. Therefore, if these 2 angles are equal and these 2 are already 90 degrees, then what do you have? Similar triangles. And what have they told you in the question beautifully? It's a 3 times magnified image. So if this is 1, then this is 3. And they've also told you this is 10. This little length is 10. And they've asked you what this length is. What do we know? The ratios have to be similar. That's why it's a similar triangle. The ratios are, they're proportional. All the sides are proportional. So if that is 1 and this is 3, if this is 10, this has to be 30 centimeters. And great, we're done, right? Yeah, that's pretty much what the question asks. Where is the image located? 30 centimeters away from the pole of this mirror towards the left side. So if you represent this as with the convention that you've learned, it'll be minus 30 centimeters. In other words, this minus 30 will only convey what? That the image is formed to the left of the mirror. Can the image ever be formed to the right of the mirror? Well, in one sense it can, right? Because when the image is virtual, it appears to be on that side. So that time we give it a positive value and call it a virtual image. Great. So in this case, it's a real image, it's magnified, and it's 30 centimeters to the left. Now, once you've worked this much, right, what you will not do is do this over and over again. When you see this question, what will you do? You will know that V by U equals 3 times magnification is given, right? 3. What has been given to you is U. So you'll write V by 10 equals 3 Therefore, V equals 30 centimeters. And that's all you need to do. Yeah, that is how we'll officially do it. This was our way of just going back into some of our concepts with this question as an excuse, right? So the minus 30 is going to come because you know it's a real image, therefore it's going to form on this side. So we're done with this question. So now let's look at this question here, which says, which of these is most suitable for reading? A concave lens of focal length 50 centimeters, a convex lens of focal length 50 centimeters, a concave lens of focal length 5 centimeters, and a convex lens of focal length 5 centimeters. Now, what is more important is to know how do we go about answering a question like this, or even understanding a question like this. So what do they mean by which of these is most suitable for reading? What are you trying to do when you're reading something? We are trying to get a magnified image, right? So the first condition is we need something which has a magnification. And what do we know? Let's look at a concave lens, right? What does it do? It diverges the rays. Therefore, if you project them back, you'll get a... That's right. So if you, in your point of view, it's going to diverge the rays. The rays comes like this, it diverges, comes back. You have a point there, right? So then it always provides only a image with less magnification. That's a problem. So I cannot use a concave lens. It just doesn't make any sense, right? Why would I want to make the small letters even smaller? Just doesn't work, right? So if as an image, this is what a concave lens would do, right? Put an object, it takes it out. So somewhere over here is where the image is going to be formed, always smaller than the actual object. So it's a problem. So what do I know then? I'm left with the choice of a convex lens. And I know that for a convex lens, also to get a magnified image, so if you were to take the lens accurately, then your focus would fall somewhere over here. Yeah, and okay, great, that should do. So then you draw this that way. And so that you have diverging rays. This is the right way of doing it. And this is going to go back. Now why we do this, we know. Why do we project it backwards? Because somebody sees it here. They are going to imagine it coming from a point over there. So I know that the more I do this, the more closer I keep it to the convex lens, I'm going to get a good magnification. Great. So the choice now is between 50 centimeters and 5 centimeters. Now let's look what happens, right? What happens if I make this focal length somewhere around 50 centimeters, right? A very, very large focal length. Let's compare these two situations. So convex lens here of say 5 centimeters and another one here. We'll compare these two of say 50 centimeters. Right? I've drawn them as if they look similar, although they won't. So over here it's going to be very nice. So 5 centimeters is going to be its focal length. And let's see what happens here. Compared to on a scale, right? Let's make this 50 centimeters, right? So that's a lot less than 50 centimeters. If this is 5, that's definitely not 50. It's much lesser, but still see what happens. So keep an object here. You draw the diagram, you begin to observe that you get an image somewhere over here. It's very, very vaguely drawn, but yeah, you get an image somewhere over here. But if you were to try the same thing out here, right? Take an object, place it somewhere over here. But of course, now the focal length is 50 centimeters. So what's going to happen? That line has to be drawn to pass through that, right? So here, of course, it went that way, 2 rays. So here it's going this way and the other one's going that way. They are not diverging as much as in this case, which means that if you extend them, they'll meet somewhere over here. In other words, the larger and larger this focal length, what pattern do we observe? The lesser and lesser the magnification, right? Because this line is going to become more and more horizontal. It's going to become more and more horizontal. The larger and larger the focal length becomes, which means the image is going to become closer and closer to the actual object itself in terms of size. Is that what we want? No, right? You want a good magnification. So the smaller and smaller the focal length, the better is going to be the magnification. So which one do we choose now? That's right. The convex lens of 50 centimeters goes. The 5 centimeters what wins finally. So to read, a convex lens with a focal length of 5 centimeters would be really suitable. Okay. I'm starting the next question now. This is a really interesting question. Okay. What happens when we cover one half of any lens or mirror with a black paper? Now this has always fascinated me, right? if you take a mirror, let's start with a plane mirror, no? Take a plane mirror. And if I were to, let's say this is my mirror. And you could stand somewhere over here and see yourself in this mirror. What if somebody covered it off, right? Covered a good part of it with black paper. So great, I'm going to now that I've put this black paper and covered half of it, the question is, will half the image disappear? Now, it need not, and we'll show you why, right? What this black does is that this part of the mirror is lost for us, right? That's practically what it is. So if I were to do the same thing in say a convex lens, what would that mean, right? It would mean that, say I cover this part with black paper, that part doesn't do any of its work anymore because it's covered with black paper. But does that mean I won't see an image? Let's find out. So we know that if I have an object somewhere over here, it's going to go like this. There's one ray that's going to take it this way and somewhere like that. And another ray that goes like this. Now are these like the only rays? Now these are the rays we took for convenience, right? There are going to be so many more rays that are going somewhere. One of them is going to go somewhere over here and reach that point. The one thing we know is all rays that begin over here will end their journey over here. They'll meet again over here. They'll not end their journey in one sense. They'll actually meet again over here. And that's what's the meaning of an image, right? When the rays starting from a particular point reach another point, they all begin at a place and then end at a different place. Again, they meet again. Then it's called an image. So how exactly does this black affect our situation now? There would have been certain rays that would have come here, which would have reached this place if this place had the convex lens, but now it doesn't. So what happens to these rays? They just go, or they get absorbed over here, right? Because we've covered with black paper, they get absorbed over there. So where do they go? Nowhere. They die over here itself. So what happens as far as our image is concerned? The top part of the image does appear over here. What about the bottom one? Yeah, there are going to be a few rays that go like this and come over here, yeah, and reach this point. Somehow or the other, reach the point where it should have reached. This point's going to form an image here, right? So no matter what happens, right? Even though I've covered like this entire thing with black paper, even if I cover more of it with black paper, the brightness of this image will reduce. Why is that? By brightness or intensity, in other words, the number of rays that contribute to creating this image will reduce, but the image will be formed in its entirety. Complete image will be formed, except that its brightness or intensity will be lesser. Now, this is just to dispel a misconception that, if I take away the bottom half, if I take this off, then will only half the image be formed, or questions like that. So the answer is no. The entire image will be formed, brightness reduced. Same case in case of this mirror. Some of the rays that would have reflected off over here are now not there. Only the ones that are reflecting off from this part of the mirror are there. So for each point, the image is still going to be formed, but the number of rays that form that image are now reducing. So we could do the same thing with a concave mirror as well, concave lens as well, with a concave mirror as well. We could do all of it and we could prove the same thing. So the image is formed fully, the intensity is reducing. Next question is, an object is placed at a distance of 10 centimeters from a convex mirror of focal length 15 centimeters. Find the position and nature of the image. Oh my God. Why do they ask such boring questions? No. This question is boring because we've spent a lot of time to make it boring. We've actually understood enough to make such a question boring, and we'll show you how. Now, why is this question boring? Because it's too easy, right? That's why it's boring. So we could ask much harder questions, but it's fun to solve questions that we already know how to solve, right? So an object is placed at a distance of 10 centimeters from a convex mirror. We don't need the diagram, actually, but we'll draw it just for the fun of it. So an object is placed 10 centimeters away, 10 centimeters from a convex mirror. So there it is. Of focal length 15 centimeters. So we'll mark off one more point here, just so that we know it's 15 centimeters. So approximately over here, that's our focal length. What is the question? Find the position and nature of the image. Now, why we drew this is in our mind so that we have a vague idea at least of how the image is going to be. So we'll do that, right? So let's take the convex mirror. So what's going to happen? It's going to reflect off of some point over here, right? It's going to reflect as if it's coming from that point, which is 15 centimeters away itself. And that's one ray. we need to look for the other ray, right? So let's try and find the other ray. So to do that, we need the 2f, which we need to take on the other side, so that that ray behaves as if it's coming from there. So what ray do we take? So a 2f is going to be approximately here, right? Yeah, if this is f, 2f is going to be approximately there. So that ray that would have passed through that, right? It's a little very, very bad line, but yeah, will come back exactly the way it went, because it's passing through the normal of this big circular or spherical mirror. So these two rays are now diverging. So will they ever meet? No. What kind of an image can they form? A virtual image. So then it would form somewhere over here. So we can see that it's going to be kind of a virtual image, an erect image formed on the other side. We kind of have all this, right? We don't have to do this though. What we needed to have done is to have been able to read that question and immediately represent it this way, right? What formula will you use? Mirror formula. And that's why this question is boring. We've spent a lot of time understanding mirror formula. Now our job is just to apply it and get the answer. So what is the mirror formula? 1 by V plus 1 by U gives 1 by F. Now we did spend some time understanding why this is true by taking similar triangles. And we have this diagram right here to help us, get an intuition of this. What is important in this formula is that this and this, these quantities V, U and F should have signs for them. And the signs will be such that if the object is towards the left of the pole, which is the pole of the mirror, then the sign must be negative, and if it's plus, if it's on the other side, it must be, if it's towards the right, it must be positive. Now we know why we did this, right? To make it so that all the answers look more beautiful and all our formulae look more beautiful. So in this case, what is going to be our U? 10 centimeters? Or, that's right, minus 10 centimeters, because it's towards the left of our convex mirror. So if I were to write this down, if we put our values here, so this U becomes minus 10 centimeters. And what's our F going to be? Yeah, for a convex mirror, is the focal length positive or negative? If you notice here, right, it's appearing as if it's coming from the focal length or the focus on the right side. And right means positive, right? So that's our convention. Right and up positive, left and down negative. So you're right. Therefore, this is going to become plus 15 centimeters. And what we need to find is our V. Great. So what does this become now? I'm going to write this down over here. 1 by V equals, we'll use a different color, 1 by 15 centimeters. And that's on the other side. I need to take the U to the other side as well, right? So the U over here goes to the other side and thereby becomes plus 1 by 10. So it was 1 by minus 10 on this side, 1 by minus 10, and this was 1 by plus 15. And we've taken this to the other side, therefore it becomes 1 by plus 10. That's what we've written here. Now this becomes a very easy problem to solve. 1 by 15 plus 1 by 10. Now what is that going to be? If you were to have that over here, 1 by V equals, we'll cross multiply, yeah, 10 plus 15 divided by 150. Now this is like the worst way of doing it, okay, but then yeah, let's do it this way. That is 25 by 150 or 1 by 6. Right, 25 by 150 is 1 by 6. So 1 by V is 1 by 6. And look at it, there is no negative sign there, okay, it's positive. So therefore V is going to be 6 centimeters. Great. Now what have we come to? That V is plus 6 centimeters, right? Even though it's not there explicitly, we know it's a plus 6 centimeters. Now what does this mean for us? That the image is formed to the right of the convex mirror, which means that it's going to be virtual. Yeah. And clearly, you can also observe one more thing. The U was 10 centimeters, right? And the V is only 6 centimeters. So the object is going to be, is the image going to be magnified or diminished? That's it, it's going to be diminished. Because the magnification is V by U. And in this case, V by U is going to be less than 1, right? 6 by 10 is less than 1. And the magnification is going to tell you, this whole thing also tells you that the image is going to be erect, right? Because it's on the other side, it's virtual, therefore it has to be erect. And for, of course, it's V by U the magnification is V by U, but with its signs, it's going to be minus V by U. So therefore, in this case, you're going to get a positive value for the magnification, yeah, but a value less than 1. It's going to be 6 by 10, which is approximately 3 by 5, right? 0.6. So that's what you have. So we've made a good amount of inferences about this, but what was the actual question? Find the position and nature of the image. Position, plus 6 centimeters. Nature, erect and diminished, virtual of course. So these are the inferences that we have made. When we say magnification of a plane mirror is plus 1. Okay, what do we mean? This is what we mean. Right now, we've always been telling this, right? That if you don't already know, we always say that the plane mirror forms an image that is exactly as far away behind the mirror as the object is. And the size is same, it's erect, it's virtual, same size, right? Size is same. So all of that. How do we say this, by the way? We'll take a quick glance into how we know this. So if you were to take an image, right? Let's take a point image to begin with. It's simpler because once you know what's true for a point, you can always extend it. So how do we see an image for this point? One ray, some random ray is going to go hit the mirror and come off. Following, angle of incidence equals angle of reflection, our most basic rule. Another ray, because we need 2 rays at least to locate one point, right? So that's going to go this way and that's going to come out somewhere like that. Again, following, angle of incidence equals angle of reflection. So at all these points, there is a normal that is there. Great. So somebody over here is going to see 2 divergent rays and their brain is going to tell them it's coming from somewhere behind. But yeah, so the question now is, if these 2 distances are the same, right? If those 2 distances are the same, this and this, then these 2 triangles are going to be congruent. Yeah, even though they don't look like that over here, it would ideally look like this. Right? One triangle here and another triangle here, where this angle is equal, this side is equal, that side is equal. We are done already, right? Yeah, we're already done. These 2 have to be congruent, which means what? That this image, this point is going to be formed exactly as far away as the other point, if this is the mirror. Now, why are we going into all this is to show that for a mirror, in the case of a plane mirror, neither convex nor concave, nothing, just a plane mirror, every image, right, if this point was formed here, then this point somewhere over here will be formed here, and so on and so forth will be formed over here. Clearly showing that the object size is going to be exactly equal to the image size. And what is magnification? Image size by object size, right? That is what is magnification. That's how we define it. So that if this value is greater than 1, we know the image is larger than the object. If it's less than 1, if it's greater than 1, image size is greater than the object size. If it's less than 1, object size is greater than the image size. And if it's equal to 1, we know that these 2 are equal. Okay, I don't know how that disappeared. Object size. We know that these 2 are equal. And for a plane mirror, that's always true. And that's what we mean when we say the magnification of a plane mirror is plus 1. That the image and the object are equal in size. That brings us to our next question. Find the focal length of a lens of power minus 2 diopters. What type of lens is this? So when somebody tells you this, you know what this tells you? When somebody tells you my power is minus 2, you have a lot more information than you used to have. When you say minus 2, like, oh, okay. And that's all we could say, right? But now we can say a lot more. First thing we can do is find out what the focal length of that lens is. And how do we do that? We do that by simply knowing that the focal length and the power are connected, right? The power is just a very, very convenient way to talk about focal length. And how is it defined? Power of a lens is defined as 1 by the focal length. And that's how it's defined. So when anybody told you what is your power, in your mind, you know that it's 1 by the focal length in meters. Gives you power in diopters. How do we spell this word? I think it's DERES. Yeah, diopters. That's what I think it is. Yeah, that's why we always use, one alphabet so that we don't have to worry about these spellings. So you have power equals 1 by focal length. They've given you the power, asked you the focal length. Now, that is a question that is insulting, right? Yeah, but we'll still do it. Minus 2 is the power. That's equal to 1 by the focal length in meters. Yeah. So what are we going to do now? I was repeating that part because Karthik barged into the room. So yeah, so what we have here is minus 2 diopters is equal to 1 by the focal length in meters. Therefore, focal length is what? I'll write it over here. F equals 1 by minus 2 meters or minus 1 by 2 meters. And what is 1 by 2 meters? Half a meter, right? Or 50 centimeters. So that's the focal length. If somebody says my power is minus 2, what they're saying is that their focal length is minus 50 centimeters. What does this minus sign mean, by the way? It doesn't look very good to me. Yeah, what does it mean? Going by a sign convention, we know that which lens has a negative focal length. So if you don't have to remember this, right? We can just draw it out and find out. So if I take a concave lens, like over here, I know that any ray that's coming here is going to get diverged, and therefore it's going to act as if it's coming from a focus on the left side, and anything on the left is negative. That was our convention, right? Right positive, up positive, left negative, and down negative. So in your point of view, right positive, up positive, left negative, and down negative. Therefore, for a concave lens, the focal length is going to be negative. And here we get a negative answer. So what lens is this person using? A concave lens, right? They're using a concave lens of focal length 50 centimeters. That's what the negative sign conveys. In the next chapter, you'll even be now able to say what defect they have in their eyes. Wouldn't you feel powerful when you do that? They tell you minus 2 is my power, and you tell them you're wearing a concave lens and you're wearing it because you have such and such defect. So wait for it in the next chapter. But right now, this itself would do. You found out their focal length, 50 centimeters, and a minus sign tells you it's a concave lens. To solve one of these examples as well. So sounds like a big problem. So that's our next question. A 2 centimeter tall object is placed perpendicular to the principal axis of a concave lens, of a convex lens, sorry, a focal length 10 centimeters. So when we read this, let's draw this out and represent it, even though we don't need to. To solve this problem, we don't need to. We can use, now that we know it's a lens, right? Convex lens. In our mind, what do we say? Okay, they've given me, we'll just pick out all the important stuff for here, okay? Whenever we read a question, we're going to pick out the actual information and leave out the story. Okay, focal length 10 centimeters. That's something I'm going to use, important, right? Convex lens, I'm going to use that. 2 centimeter tall object, right? They've given me the height. Maybe there's some reason for it. The distance of the object is 15 centimeters. So all these are things we pick out. And then they've asked you to find something, nature, position, size. It's going to be simple, right? So you have a convex lens, a focal length, how much? 10 centimeters. The object is placed about 15 centimeters away. Great. So that's how it's going to look. It's about 2 centimeters tall. They've asked you to find many things. Now, do we need to draw anything out? No need, right? We don't have to, because we know something. For a lens, we know that it follows this rule. 1 by V minus 1 by U equals 1 by F. We spend a lot of time understanding this, so it makes sense for us to use this tool now, right? Because we spent some time to understand why this is true. Now, what do we do here? What is V? The image distance. What is U? The object distance. And what is F? The focal length, with their appropriate signs. So we need to put the appropriate signs, calculate, and we are done. So let's do that. 1 by V is what we need to find. V is what we need to find. Nature, position of the image. V is going to give us the position of the image. Minus 1 by U. And what is U over here? 15 centimeters, right? Can we put 15 directly? It's to the left of the lens, which means that it is negative. So minus 15 is going to be our U equals 1 by F. Now F, is it going to be positive or negative? It's 10 centimeters. Is it positive or negative? So left, right? We've drawn it to the left over here. Therefore it must be negative? No, because this ray is going to go like that, and therefore it's going to pass through the focus that's on the right side. So for a convex lens, the focus is pretty much on the right side, and for a concave, it's going to be on the left side. So because over here it's on the right side, what do we have? It's going to be positive. So what's the value? 10 centimeters on the positive side. Great. So what do we have now? We have 1 by U equals 1 by 15, 1 by V minus 1 by minus 15 equals 1 by 10. So these two minuses can go, right? Yeah. You don't have to have the minus of minus. It's plus. Therefore, what do you have? You have 1 by V equals 1 by 10 minus 1 by 15. So is this going to be a positive value or a negative value? A positive value, because 1 by 10 is larger than 1 by 15. Right? It's greater than 1 by 15. So if you calculate this, again doing it by our very, very inefficient approach, 15 minus 10 divided by 150. It's going to be 5 divided by 150. Great. And what is that? 5 divided by 150 is 1 divided by 30, right? Because 5 and 15 can be cancelled out. I know I'm doing this as if it's a big task. I'm doing it just because even if some of us are not so particularly comfortable doing all these divisions, we know how to do them. So instead of jumping a few steps, we're making sure we're doing every single small step the way we will do it as children, right? So 1 by V equals 1 by 30, giving us V equals 30 what? Centimeters. Great. So the fact that it has a positive value means that we're going to have an image forming somewhere on the right side, and it's going to be, what kind of an image is it going to be? Well, we don't know. Or do we? Yeah. So let's first look at this diagram and let's kind of infer certain things, right? So if you draw this out, it's going to, one of the rays is going to go like this. We've already drawn that ray. So it's going like that. And the other ray is going to go like this. Yeah, that's our second ray that we choose. And they'll probably meet somewhere over here. And this passes unaffected because it's passing through the pole. So if you take that image right now, it's going to be somewhere over here. Now, even by looking at this, it looks like we're going to have some magnification, right? Yeah, it looks like that. So first thing we found out, position of image, right? 30 centimeters away. So where was the object? 15 centimeters away. Where is the image? 30 centimeters away. So now, how do we find our magnification? Is it magnified? Looks like it is. Yeah. And what do we know about magnification? It is V by U, right? The magnification for a lens is going to be V by U, even with the signs, isn't it? So what's going to be our answer? Our V is 30 centimeters, right? And our U is minus 15 centimeters. Therefore, 30 divided by minus 15 is going to be minus 2. So the magnification is coming out to be minus 2. Oh no, what does that mean? Yeah, all negatives are going to have some meaning, right? So the magnification being minus 2 means what? That one, the image is larger than the object, okay? It is larger. Yeah, clearly, by a factor of 2. So if this was 2 centimeters, this length is going to be 4 centimeters. An image twice as large. But what does this minus mean? I don't want that minus there. It means that the image is inverted. If it had been erect, you would have got a magnification value that is positive. But the negative sign here shows that it is down, right? We told that left and down are negative. So here, in the magnification case, the negative sign implies it's down. Therefore, it's an inverted image. So the minus 2, it's beautiful, right? The sign convention is so beautiful because it tells you that not only the size of the image, but also whether it's inverted or erect. So minus 2 means it's size of 4 centimeters, twice the size, but inverted. So nature is done, position is done, and size is done. Okay, position was done, size was done. Nature inverted. Anything more we can say? A real image, right? In fact, all inverted images are real. So we've done nature, position, and size, which means we've done our job. Magnification is what in fact gave us that. We didn't do it the other way, right? We didn't find the size and then go for magnification. We found the magnification and that gave us information about all of these. Let's begin taking some of the questions from your textbook, right? Now it's time to go a little bit further, just for the fun of it, and ask you a few questions. Now one of them is, as you can see here, right? If I take a concave mirror, and if I take my F over here and my 2F over here, and place an object at that 2F, but in this way, right? Not the usual way. Now it's not really an arrow. We always have objects that are like this, right? One-dimensional objects. But now we make it a two-dimensional object. It's going to be a C written this way, right? So if you have a mirror here in this plane, the C is going to be that way. So if you turn it, it's going to be like that. Yeah. So the C is going to be not like this with the mirror, but like that. So the sea and the mirror are parallel. Then the question is, how is the image going to be formed? It's going to be formed at 2f, of course. But is it going to be like this itself, or is it going to be an S that's going to form? What's going to happen? Now, how do we solve such a question, right? It's a spherical mirror. We usually treat this mirror as if it's a line. It's a 2D line. No, but it's not, right? It's actually spherical. So it exists in a plane like this, right? The mirror is going to be like this. So if I keep a C in front, and if the mirror is like this, then how am I going to find the image? We're going to treat the C as if it's made up of many small points, right? So if one point on that C is going to form an image right below, right? So symmetry here, right? If this was you're going to do some imagination now. That line is the principal axis and the mirror is right here, right? So what do we see? A C over here forms an image, hits the mirror and forms an image below here. Then as the C continues like this, that's your C. Another point here would hit the mirror here and form a point there, right? And this point here would hit and form there, and so on and so forth. So what's going to happen? Top point of the C, if this is your C, the topmost point of the C is going to form an image right below. The point of the C, rightmost point is going to hit and form an image somewhere over here. And the bottommost point is of course going to form it right there. So if I draw this out here, it's going to look like this, right? The bottommost point goes and comes back, forms an image over here. The topmost point forms an image over here. The rightmost point is going to come and form an image over here, which would in that place look that way, so that you have an image that looks like this, right? In other words, what are we saying? If all images that were there invert this way, right? Because we know that if you keep an object at 2f, the image forms at 2f inverted same size, right? So if I keep upward object, it's going to form downwards. If I keep rightwards, it's going to form that way. That's all we're arguing. So if I kept a C there, the image that is formed would be like this. So the C would be here, the other C would come here. Thereby, the object would be this, the image would be this. So you would see something like this, with the object and image being this way. So that was our question. Now coming to one of the most interesting questions here, right? Let's imagine you're a bee or a dragonfly floating above the swimming pool. And you look down at the swimming pool and you see, you know that, or probably you don't know, yeah, you're a dragonfly. But yeah, we know that the floor is flat, right? Mostly the floor is going to be flat. But if you look at the floor, what surface will you see? You see a flat surface? No, first of all, why is this even a question? Because the rays of light from the bottom of that surface are going to come up and they're going to bend when they leave water and enter air. So it's going to be something like this. So that is your water. And you're the dragonfly looking from top. Yeah, so that's a dragonfly, if you may pardon my drawing. Yeah. And the rays of light from here, let's take a point over here, are going to come this way and bend, right? Because of refraction. Oh no, is that the way to put it? Are they bending because of refraction? No. They are bending because of many principles where finally you go down, you won't know why they're really bending. But this phenomenon is called refraction. Yeah, so it's called refraction. It's going to go that way. Therefore, something's going to happen. So how do we attack this question? The question of the mysterious swimming pool floor. Is it going to be flat or is it going to be something else? Let's see what happens. A point over here, right? Let's say that light leaves the surface over here. It's going to come like this and bend that way and reach the dragonfly's eye. Another point here is going to come like this and bend that way, therefore reaching the dragonfly's eye. A straight point is going to not bend at all, right? Straight, it's just going to go straight. Because the angle of incidence is going to be 90 degrees, in this case 0 degrees with the normal, therefore 0 degrees out there. So similar, so on and so forth on both sides, symmetrically, right? So the dragonfly's eyes are going to get rays in this manner. Coming from here, they're all going to bend in the manner that's shown. So which of them is going to bend the most? The further and further away a ray is, the larger and larger it's going to bend. So a ray over here is going to bend even more. Now why is that important? Because as far as the dragonfly knows, it does not know that all these rays exist. It just doesn't know, right? All it sees are the rays that reach its eyes. So what will it infer? It'll infer that this is coming from here, this is coming from here, and so on and so forth, so on and so forth. What will it look like? Yeah. This one seems as if it's coming from where it is. This one's a little bent because it would have come from here somewhere, but then it got bent, so it appears as if it's coming from here. This appears as if the dragonfly doesn't do the bending. It assumes that it's going straight, right? It came from that point. That's what we all do. So it's going to look a manner like this. Now, isn't that fascinating? What happens? For the object that's right below, the point in the surface that's right below, the dragonfly kind of figures it's going to be exactly over there. Right? A little, or rather it gets the least bending. So even if you were to take a little surface over here, the amount of apparent depth reduction that you see will be a lot lesser compared to the points on the side. So the farther and farther away the point is, the more and more it bends, and therefore the more and more its apparent depth reduces, making it seem like it's closer to the surface. So the centermost point seems the farthest away. Everything else seems closer. So dragonfly looks at the pool and it sees a surface like this. So it looks down and it goes like, oh, the swimming pool surface is like a ball. But what is it really? It's flat. The apparent depth changes with the angle. That's an interesting question as well. Now, these couple of questions we've asked finally are questions that are not usually asked. Yeah, a little more application to the fundamental concepts that we've learned.